My name is Agnese Chiatti, and I'm a PhD student at the Knowledge Media Institute. And today I want to talk about why we find it important to improve the visual intelligence of service robots and the roadmap that we foresee to allow for that improvement. So first and foremost, I think this links nicely with the previous keynote speaker, where we already discussed how robots are being used to be of assistance to humans for many tasks. For example, in our department, we're trying to implement a prototype of robot inspector that can monitor the health and safety of a building. And the type of use cases are things like checking that the fire extinguisher are correctly labeled, for example, or that we don't leave a pile of paper proceedings on top of an open fire and things of this sort. So the problem essentially becomes, before we delegate tasks to these assistants, we need to ensure that the systems are robust. And essentially what we're asking the robot to do is to make sense of a high volume of data that are coming through their perceptual sensors. And of course, there are many entry points to this problem, but we chose to focus specifically on vision. And so, for example, consider a robot that is seeing a monitor. Right, so under certain light conditions, this monitor may look very similar to a radiator to the robot. In the end, both objects are rectangular and both can look shiny under that light. But if the robot was aware also of the fact that the unknown shiny rectangular object is sitting next to a keyboard, then it would be intuitively one step closer to identify it as a monitor. So in the paper, we define visual intelligence as a robot's ability to use not only its vision system, but also its reasoning components and background knowledge to make sense of the environment. And back to the health and safety monitoring example, let's assume a robot has access to a 100% accurate object recognition system. Even in that case, the object down in the corner here would be classified as a carton box maybe, and quite rightfully so. However, this representation is not sufficient because clearly this object is being used as a paper bin in this office. And we can draw this conclusion almost instantly through the human eye. So as you can tell from this simple example, things get complicated here because we tap simultaneously across many different sources of knowledge. Part of them have to do with common sense. So this further complicates things because common sense can be hard to define and subjective. And also some things may be based on our own experience. So at the moment, the image understanding systems that we have available rely heavily on deep learning and machine learning. And these methods certainly hold value. However, they come with their own limitations. They can require lots of training data. They're difficult to expand beyond the original scope of their design. And oftentimes the type of representation they produce are really hard to explain. On the contrary, we excel at vision. So there is an incentive to take inspiration from the human mind when modeling visual intelligence. And another evidence from the literature is that more recent methods that are trying to combine machine learning with knowledge-based reasoning are showing promising results. Still, a question remains on which knowledge representation should we leverage within a hybrid method. And this needs further careful consideration, especially because, as I already mentioned, there are different and diverse types of knowledge that are involved and equally important. So based on these evidences from the literature and inspired by that, we ask, what are the epistemic ingredients that a robot needs to exhibit high performance visual intelligence? And by epistemic ingredient, we mean a set of knowledge properties that the robot needs access to and a set of reasoning capabilities as well. And then provided that we find these requirements, which one should we prioritize? Let's say we create a real world robotic application. So these first two questions guide our requirement analysis, which is the first contribution addressed in our paper. And then in the second part, we also use the framework to evaluate the state-of-the-art knowledge bases, not only in service robotics, but also in linguistical and encyclopedical knowledge. So what do we know about the human visual cognition or human learning, really? what we know is that we're really good at creating this sort of mental blueprint of the environment, and we're also good at maintaining it over time as the environment changes and as we learn new concepts. Not only that, but within that world, since a very early age, we're already aware of sort of the basic physical rules that govern this model. And also, not only do we recognize the different functional parts that compose humans and objects, but also we can segment one object from others that may be nearby. What is even more fascinating is that at the end of the day, all that we see is cast at the back of our eye as a two-dimensional image, and then we construct the 3D mentally on top of that. So there seem to exist some preferred 2D views in terms of colors and shapes that helps us categorizing objects correctly. And also another features that was mentioned in the keynote speech as well is our ability to perceive the interaction between people and people with objects, which we may call affordances. And also the thing that we maintain different representations depending on whether the object is static or movable. And all this happens really fast, so there is an incentive to take advantage from methods that are fast at inference time, like machine learning-based methods, but combine them with methods that provide richer representations. So given these top-down requirements from the literature, we also wanted to ground our analysis in our own lessons learned from prior experiments. So we considered an experiment where we used a purely machine learning-based algorithm, and specifically we considered the regions that that algorithm could not classify correctly. So let's say a rubbish bin, for example, was mistaken for a coffee mug. We would take note of that incorrect prediction and make hypotheses around the fact that knowing, for example, that the mug is typically smaller than a bin would have helped. And also that typically bins are found on floors, and that doesn't always apply to mugs as well. So let's say we find a second case where all the same hypotheses apply as well, but also knowing that there's clearly an indication that that's a paper being written on the object. We would also add another column to indicate that reading is another important capability in this case. And then column by column or requirement by requirement, we count how many times this was found relevant and divide it by the total number of errors. And in this way, we obtain some percentages that are also summarized in this picture. And these percentages give us an estimation of the relative importance of each ingredient in our own use case. And as you can immediately tell from the picture, intuitive physics per se has the potential to improve our object recognition capability quite a bit, especially when it comes down to comparing the relative size of objects. But at the same time, there are other features like the natural vertical or horizontal orientation of object, or the shape, characteristics, or color features that are more a mixed bag. It depends on the type of objects. They can be more helpful or misleading. One thing that we couldn't capture through this experiment is the role of causality. That's because we were focusing on object recognition, and causality is likely to come into play later on as we've classified the objects already and we want to reason on the image as a whole. Same goes for affordances, because only a subportion of our test set actually depicted interactions of humans with objects. But if you consider only a subset where we find affordances, this 9% here would grow above 50%. So this exercise also helped us identifying another ingredient which was not foreseen in the beginning, which is the ability to read text from images. And then we use the knowledge properties that we identified as needed to check the coverage that is already provided with state-of-the-art knowledge bases. And here we include not only state-of-the-art knowledge bases in service robotics like NoRob and its fellow platform OpenEase, but also linguistic sources, encyclopedical sources, and other multimodal sources that link imagery with semantic as well. So first we check, do these sources provide links with the WordNet taxonomy? And most of them do, which is great to favor the linking of different entities across those different sources. And then we evaluate from 1 to 3 dots their coverage of each one of the requirements we identified prior. And as you can see here, for all the requirements, there is only a partial coverage. Sometimes this has to do with the fact that maybe only a limited subset of objects is being represented, or for example, in intuitive physics, there can be sources that encode explicitly the physical fabrication material of the objects, but not its dimensions. And particularly remarkable is the lack of explicit representation for the static versus moving or dynamic nature of objects. And lastly, we also rank the accessibility of its source from partial to adequate to high, depending on the type of navigation interfaces and APIs they expose. So based on our own analysis, our take home was that first and foremost, the awareness of the relative size of objects seems to be important in object recognition. And also that ShapeNet, among others, can provide for part of this knowledge. So we're using these insights to, at the moment, develop our own reasoner that can take the size of objects into account to correct the prediction of a machine learning algorithm. So let's say this fire extinguisher was mistaken for a bottle, with the awareness that in fact the object is occupying a larger space or volume, and with the knowledge that typically bottles are smaller than fire extinguishers, we could hopefully correct this prediction. So to wrap up, I show you the different ways in which machine visual intelligence is actually inferior to human visual intelligence. And based on this premise, we have defined a framework of requirements to improve the visual intelligence of service robots. And also we wanted to ground this framework in our own use case and in a practical real world scenario. And we used the same framework to evaluate as well the state of the art in terms of knowledge bases. And the idea is to provide a research agenda not only to improve the knowledge representations for robot vision, but also to choose which components to prioritize. And essentially, we're using these same insights at the moment to develop a sites-based reasoner, and as well find a strategy to reconcile the results of different sub-reasoner in a meta-reasoning architecture. With this, I conclude my presentation. Thank you for your attention, and I welcome any questions you may have.